Marc Chardin is our speaker today, from Sorbonne University in Paris, and he'll talk about schemes in products of projective spaces.
Thank you very much, Ben. So, first I wanted to show a picture and say a few, whoops. Ooh. This was working. Yeah. Say a few words about Jürgen. He was as everyone knows, he passed away months ago, and I had a lot of time, a good time sharing math with him. He had a really huge passion for mathematics that he was sharing with so many people around the world. So, well, I was expecting to see him soon in Mumbai, but this will not happen. And well, it was really a good friend. Okay, so I just dedicate this talk to him. Okay, so I will speak about schemes in product of projective space, and this is based on work with many people along time. I worked with Nicolas Bodbol, I worked with Laurent Buzet on that, with Frank Roncroix, with Raphael Honda and José Naiton, and with Navid Nemati. So, and of course, many other people work on that. So I will not put names, I think almost nowhere, but this is work of many people that I will present in this talk. The few things that are original are collaboration with these people, but it's mainly a presentation. Okay, so let's start about that. So product of projective space, I will work, at least at first, the second part will be more illustration, so it will be over a field, but for general purposes, you can work over basically any commutative ring, and you consider a multigraded polynomial ring of that, or standard graded. So standard Z grading means that you have you have a collection of variables. Each one have a number of variables. Let's call it Ni, and you have R collection, and each degree is one of the canonical. The degree of each set is one of the canonical generators of ZR. Okay, that's the standard multigrading, and we'll see that for cohomology purposes, the very important idea is the idea that define the anti-set in the product, and this is the product of the ideal generated by the different set of variables. And one can see that as just the ideal generated by elements of degree 1, which means 1, 1, 1, 1 in the ring. And so I will denote by P for simplicity the product of projective spaces over A. So this will be of dimension n1 minus 1, etc., to nr minus 1, and it's product of spec A. And now, what is so I'll first present a couple of things that are pretty similar to what happens in the projective space, and then I'll point out the differences. So the first thing is that, as in the projective space, somehow you have a one-to-one correspondence between the subscheme of this product and the graded ideal, ZR graded, so that respect this multigraded, that are, saturated, but now with respect to the ideal B, which is this product ideal, okay, and that defines the empty set. So this is pretty similar. And also for sheaves, a quasi-coherent sheaf on P correspond not in a unique way, but all of them are given by graded modules, okay? And if you have a finiteness condition, so if the sheaf is coherent, then two different modules give the same sheaf if and only if the modules agree in degree big enough. So this is also pretty similar to the usual case of one projective space. Of course, this holds for one, but holds for several, okay? Now, if A is Noetherian, okay, and that's a basic case we want to understand, and M is finitely generated and graded, it will always be graded, then you can make a minimal free resolution. Of course, if A is not local, there is not a unique one, but you can still speak about a minimal free resolution, and this exists. And by minimal, I just mean that if you drop one of the generators of one summand, so if you, for instance, drop a generator of fi plus 1, the image do not generate any more fi. So it's a weak notion of minimality, correspond to the usual notion if A is local, but this always exists, over a Noetherian ring, even if you're not local. And let me first give you a definition. A definition will be for the support. I mean, it means support with respect to the ZR grading of a module. It's just the degrees where the module is not zero. And the first thing is we want to understand the degrees of generators in a free resolution. And the first thing is to link this to the Tor modules. So the first thing is that if you have a finitely generated gradient module and you look at any of these minimal free resolution, okay, it's essentially unique if A is local, but else you always have minimal ones. Then for any T, when you look at the support of these modules here, oops, so well, maybe I will put the subtitle. I mean, the support of FA tensor RA is just the degrees of the generators, because when you tensor by A, you kill the action of the variables. So what is on the left, the support of FA tensor A is the union of, I mean, degrees of generators of the first part up F0 to Fi in the minimum of resolution. And these degrees are also exactly the ones that you find in the support of the so many first term modules, okay? So you have this equality. Now, if you have a field, I mean, these are equal 1 by 1. I mean, so the support of the, I mean, so the degrees of the minimal generators of Fi exactly correspond to the degree, I mean, degrees of elements in tori are MA. Well, if you have a homogeneous ring, I mean, you only have this equality of these unions, okay, up to something, but that's, I mean, it gives you quite a lot about the degrees that appear in the free resolution in terms of these Tor modules. And the interest is that these Tor modules will be, I mean, related to the cohomology modules, we'll see in a moment. So let me recall what is Czech cohomology. And so first in a very general setting. So you have an ideal, a finitely generated ideal in the ring. It could be R ring, but it could be any commutative ring, and you have an R module. And then one can define two Czech complexes that you see, I mean, everywhere in the literature. The first one starts by the localization of M at the different elements at different generators of the ideal, and then goes to further and further localizations, where the maps are just somehow the trivial maps, we send an element to itself, but with some signs that make this a complex. So that's a very classical construction. But there are two versions. One starts at the localization, and the other one is augmented. You start at the module, and then you localize at the module. So you send element to, I mean, the same element, so A is sent to A over 1, or which is the same as AFI over FI, or any of these copies, okay? And then continue with the complex. So you have these two versions, and just, I mean, I will denote with two different notation these two Czech complexes. I will put a Czech on the first one, which we see is the one that will compute chief cohomology, and the other one, which is usually called, is the one who computes what is called local cohomology. Okay. Of course, I mean, I choose, and this is, I mean, a bit arbitrary. I mean, in this lecture, I will choose to start both complexes in index 0, so there will be a shift of 1 between one and the other one, okay? And the second one is just the augmentation of M to the first one, okay? Now, of course, I mean, by the very definition, I mean, you have that the Czech is equal to the local cohomology shifted by 1, except for the index 0, because it's just the same complex. And for the index 0, you just write the augmentation, okay, and the image and the kernels, and you just found that you have this exact sequence, this very classical exact sequence that goes from the V torsion of M to M, and then you have this thing that is just the kernel and the kernel module of the image is by definition H1B. So you have this classical thing. Okay, so this is very classical things. And now the important thing is that, so we return to our case. And so we have a standard graded, multi-graded ring. And we have this ideal B, which is generated by elements of multi-degree 1, 1, 1, 1. Okay, and now you suppose you have a sheaf on the projective space. This is induced, I mean, a quasi-coherent sheaf. It's given by a gradient module. Okay, and then the theorem, I mean, the result is that now for any degree in the R and every I, the I sheaf cohomology of the sheaf F twisted by mu on P is just the Chesh cohomology, corresponding Chesh cohomology with respect to B, this product of ideals. I mean, this ideal generated by things of multi-degree 1 in R. Okay, so this happens in any degree. And you also have, properties that are classical properties of one projective space is that if your ring is Noetherian and the module is finitely generated, then for any I mean, the Chesh cohomologies and the local cohomologies in every degree are finitely generated over A. So all the graded pieces are finite over A. And now if you look at the local cohomology in degree high enough, this will be 0. I mean, this is what is usually called, this could be seen as a consequence of cell vanishing. Okay, and the same holds for the Chesh cohomology if you have a positive index as a consequence. Okay. Now, if A is a field and M is finitely generated, okay, then you have also the classical so-called Grothendieck-Stern formula tells you that the Hilbert function could be computed. So this is the dimension over the field now of the graded pieces. Okay, this is a polynomial plus the alternated sum of dimension of local cohomologies. And now it's a local cohomology supported in B in this degree mu. So this tells you that the difference between the Hilbert function and the Hilbert polynomial can be expressed in terms of this local cohomologies. Okay, and P is the Hilbert polynomial, so it's an integral valued polynomial in R variables. Okay. Now, by 3, you also get that this polynomial, you can express it, and by the sequence that was on the previous slide, as the alternated sum of the dimensions of Chesh cohomology in any degree, or as the alternated sum, of course, as we have seen in the above term, is the same, of the dimension of the sheaf cohomologies in any degree. Okay. The other thing is that and so this is very similar to what happens over Pn. So the degree of this polynomial, it's a it's a polynomial in R variables, is again the dimension. Of course, one can take that as definition, but the usual definition is more like, by different things, by Noether normalization, or you can define that by transcendence degrees, or you can define that in many ways, or crude dimension. And so this dimension is given by the degree of the polynomial, so that's also very similar. And now, if you look at the homogeneous part of highest degree of the degree dimension of Z, that's now a form. The coefficient of these gives you multi-degrees, okay? And they are also called mixed multiplicities, okay? And because, if you have a scheme in a product of projective spaces, you don't have just one degree, but unless you, like dimension 0 or something like that, you have a multi-degree that corresponds geometrically, to what happens by cutting by product of linear spaces coming from the different factors. Okay, now the cohomology of P, of the product of projective spaces, I will explain how one computes this, and it's quite different than in the case of one projective space. So first, if you have, I will give a notation. So if you have one set of variables that calls these xi for and bi, the ideal generated by the I set of variable. Okay, now, this classical computation of cohomology for just one projective space, if you want, or for, polynomial ring over any ring, tells you that the cohomology with respect to the sum of these, which we given by some variables, is 0 unless the index is equal to the number of variables, and else it's the inverse of the product of these variables times the polynomial ring in the, where you invert the variables corresponding to one appearing in BI1, BIP, and you keep the other one as in the original ring. Okay, so that's very classical thing, so, but it's very concrete description of that. Okay, and now for the ring itself and cohomology with B, it's just a direct sum of these. Okay, for the different possibilities BI1, BIP. Okay, so you have many cohomologies that correspond to taking all cohomologies with respect to different sums of variables. And now, of course, this thing on the right, HQ plus P minus 1 with respect to BI1, BIP is 0 by what is above, unless Q is of this form. Okay, so you have this, I mean, you look at the contribution that you can have by taking the different BI1, BIP, and this cooks the cohomology of the ring. So let me give just one simple example that will look. It's a case of two projective spaces. Okay, so the first case, and then let's say that the degrees are different. Then the cohomology will be 0 unless you, I mean, it will exist only in 3 degrees, which are the, I mean, first the number of variables in the first pack, the number of variables in the second pack, and the sum of these two numbers minus 1. And the first, I mean, the cohomology with respect to B, if you take the n-ith one, it will be the one corresponding with cohomology with respect to BI, which means that essentially you use the description above where you invert the variables in BI and keep the other one as they are. Okay, and the other one is at the level n1 plus n2 minus 1, and will be the cohomology, corresponding cohomology in all the variables. Okay, so like in the projective space. Okay, so that's the thing. And so now you have, I mean, in place of having, in this case, for instance, one cohomology of the ring, you have 3 models for the cohomology of the ring. And when you have more factors, you have more and more cohomologies. Okay, so that's quite different. Now let me recall some basic things about the local cohomology. And the first thing is that if you have 2 finitely generated ideals, then you get the same cohomology, I mean, with respect to A and B. So if radical of A is radical of B and A and B are finitely generated, then the ith cohomology of these 2 complexes are isomorphic. And with respect to grading is A and B is graded. And the same, of course, for the cohomology where you start one step further, one step later. I mean, all the Czech cohomology. So these only depend on the radical of the ideal you choose, and that's an important fact, very well known. Now you also have the following 2 things. The first one is that if for any I and any module M, then, and that's just a remark, I mean, well, if you look at how these are built, you see that the tensor products of the Czech complexes with respect to B1 and BR is just the Czech complex with respect to B1 plus BR. Of course, on the left, I take generators, and on the right, I just put the generators one after the other to have an equality of Czech complexes. I mean, this means I take the generators and I put them one after the other. Okay. And the other fact that's also interesting that is maybe less known is that if you take the tensor product of the other Czech complexes, where you don't start with the module but with the localization, then this is not isomorphic, but it's quasi-isomorphic. So the ith cohomology of this tensor product is the ith cohomology of with respect to the product. Okay. So you have a quasi-isomorphism between the ith cohomology of the tensor product of the Czech complexes that give you sheaf cohomology and the ith cohomology with respect to the product of the ideals. Okay? And if you want to have the one with the local cohomology with respect to product, you just augment this by the first map that sends M to the first guy there, with to all localization. The first element of this tensor product is just all localization and all products. So you have this natural augmentation map, and this enables you to compute this cohomology with a complex. Of course, one can compute the Čech cohomology in the product by taking the Čech over the generators of the product, but that's a much bigger complex. So it's usually more, I mean, it's a shorter complex at the same cohomology. Okay, and on top of that, this, and I will explain how we use that. I mean, this complex here is a subcomplex of the other one. Okay, because I mean, you just you can look at that in. I mean, you just take the subcomplex where when you have something with in C dot B1 dot tensor C dot BR, I mean, when you have something with one index 0, you replace it by 0. This gives you a subcomplex. I mean, and this is this one. Okay. So let me explain. I mean, and this is something I did with Raphael Ronda and José Naït, how you get these, I mean, this construction from a theory of multiple complexes, because this is maybe not so common. So explain in usual text. I mean, so a double complex, so everybody's used to double complex. So it just means, I mean, modules and arrows like this, where all lines are complexes, or columns are complexes, and squares are anti-commute. So there's two possible choices, anti-commute or commute. I prefer to take anti-commute for the construction, but I will explain that how one can pass to another. So double complex is just something like that. And a multiple complex would be basically the same, but I will just explain for triple complex what you do. I mean, triple complex, it means that you have objects, and so modules, typically what we do, that have three indices, let's say STU, and then you have, from each of these, you have three maps that augments one of the degrees by one. So it goes from STU to S plus 1 TU, STU to ST plus 1U, and STU to STU plus 1. So for each of them, so it will be something, and it will be indexed by these three. And maps augment, so I take cohomological one, so it augments the degree by 1. And what you ask is that all the lines again are complexes. Okay, so if you fix two indices, I mean, you get a complex. Okay, and that every square anti-commutes again. Alternative equivalently, I mean, you can just ask that when you restrict, I mean, to any, so when you fix any of ST or U, you have then a double complex, okay, when you add the other things, other indices run, okay? So when you have a multiple complex, you can totalize it like a double complex. So you take the direct sum for all the indices equal to something of the corresponding modules. And as a differential, you just sum again. I mean, so an element in C Q1, Q1, we send to this sum to the different modules here, to the three modules that you go to, okay? And of course, you extend by linearity first, okay? So that's defined totalization of a multiple complex. Okay, so let me say just because I mean, in the tertiary, you have the two, I mean, possibilities. You can ask the square to anti-commute, or you can ask the square to commute, and this is essentially equivalent. One passes from one to another by this change of sign. I mean, so if you replace the i's differential corresponding to Q1 QR by -1 to this index, okay, so then it will replace a multiple complex where all square commute by one where all square anti-commute, and vice versa. Okay, so you can do the two convention. I prefer to take anti-commute because the differential has no sign inside, but it's basically the same thing. Okay, so that's a multi-complex, and that's the totalization. And so I explain for three, but you can extend to any. I mean, just ask that when you restrict to other one, it will be a multiple complex for smaller size. Okay. So now given a multiple complex, and I will take one in the, say, positive quadrant, I assume that CQ is 0 unless Q is non-negative. Okay, so we mean that each QI is non-negative. Okay, then you can look at what is we call phase restriction. So you take the complex, okay, but you restrict to the phase corresponding to two indices being 0. Okay, so this gives you, for instance, if you have a four tuple complex, F13 will be obtained by putting, by looking at what you have, where on the first and third coordinates, you just look at the strain of where the index is 0. Okay, so this will give you a double complex. Okay, and now the thing is that, okay, the second definition, sorry, before I go to the third one. I mean, you have, for us who want to apply this to the Church complex, you have the interior of a complex. Okay, so if you have a multi-complex, the interior will just the complex that you obtain by just keeping the same module in the interior where the indices are strictly positive and replacing the rest by 0. That's a sub-complex of your initial complex. Okay. Now, the point is that the theorem is that you can compute the cohomology of the interior of a multiple complex starting from the homology of all the faces of the multiple complex of different dimensions. So if you have, for instance, a triple complex, it means that the homology of the interior of the triple complex, you can compute it by a spectral sequence process starting from the homology of the total complex, the homology of the three faces of dimension 2, I mean, double complexes that are there, and then the homology along the lines, and then the sum, okay, which is just one more. Okay, so that's a general thing. And if you apply this to Čech homology, okay, you get that you have a spectral sequence that comes from the homology in the sums and goes to the homology of the product. Okay, so that's one application of that. And this spectral sequence was already built by Ubeznik some years ago. Okay, so that's not a new thing, but the process here of obtaining it is a bit different. Okay, so now applied to M and R, M equal R and R BIs, you do obtain that the theorem before, because you obtain the spectral sequence and you have the cohomology with respect to different sums of BIs. Okay, but now with respect to multiple grading, and as we have seen, I mean, when you take the cohomology in the sum of BIs, you invert some variables and not the others. Okay, and there is just one cohomology that is not 0, which is this one. And this tells you that as you respect the grading, and two different modules never have an element living in the same degree. Because to live in the same degree, it means you invert exactly the same set of variables. Okay, so this means you have the same set of variables, but then you need to have the same index. So you cannot have, I mean, unless you have twice the same thing, invert exactly the same variables and the same index. So in this sum on the that you have on the left in the spectrum, I mean, you have elements that live. If you take different modules, you have different degrees. So that you never have a map between these guys, and it tells you that the guy on the right is just a direct sum. Of course, for a general model, it's not the case. I mean, there are things happening in the spectral sequence, but this general tool, computes for you the cohomology of projective space. But of course, it gives you other things. I mean, it gives you that in any case, you have something that computes the cohomology with respect to B of a module starting from B. So in particular, you know that if all the cohomology with respect to the sum are 0, okay, then the cohomology with respect to the product is 0. Okay. So this tells you, and so I will set the notation cohomology with respect to B of M. Okay, so this will be the support of the union of the support of the cohomologies with respect to B. Okay, and this tells you that this is inside the union of the cohomologies with respect to different sum. Okay, because this thing respects the grading. So if everybody on the left is 0, the other one will be 0. So now I just put a small notation that is, for if you have a subset of the R, I will put E star to be the elements that are less or equal to E, which is one can write E minus NR. Okay. So first, I mean, there is one lemma, and there are some results about that. And the first lemma that one can show is that if you have any ideal in this sum, okay, that is graded, then the cohomology with respect to the sum, okay, if you put the star, is inside the cohomology with respect to B. So you have an inclusion. I mean, you have more, I mean, the degrees where one exists have to be inside this one, okay? And that's a key lemma to prove the, the following theorem, okay, that relates shift inferior resolution cohomology. So if M is a graded R module, okay, then you have that if you look at the cohomology with respect to BI, and this is essentially extended, I mean, just looking at graded pieces here, extending the usual results about cohomology with respect to one set of variable. I mean, so this is essentially an an easy extension of the classical results. The cohomology with respect to Bi of M, the support of that, if you shift by the number of variables, I mean, times the corresponding degree of this variable, then this is just equal to the support of the torus corresponding to R modulo Bi. Okay. So this is essentially saying that degree by degree, you use this. You could prove that by showing that degree by degree, you use a classical thing about regularity with respect to one set of variables. Okay. So this is not so difficult to prove and not so original compared to the single grading case. The other thing, and that this comes from the lemma, is that the cohomology with respect to B is just the union of the cohomologies with respect to different BIs. Okay. Because by the thing above, you have that the cohomology with respect to M is inside this union, but these unions, I mean, again, the ideal B is always in any sum like this, so you get this equality here. And the third thing is, and this is that, I mean, as in the classical case, you have a relation between cohomology with respect to the maximum, or M, all the variables. I mean, it's a maximum if A is a field, else it's just the ideal generated by all the variables. So the support of the cohomology with respect to all the variables is the same as the union of the support of the Tor modules, okay? Now, if you take things like E star, so if you take everybody that is less or equal, because of course cohomology with respect to M typically have elements of very negative degrees and Tors exist on infinitely negative degrees. So it's things that are at most there, at most in the less or equal, in the sense that you can subtract any element n to the n for the Tors and for the cohomology. Okay. So now so this extends things about classical regularity. So about the computation, I mean, let me say a few words. I mean, so you have these two things. I mean, the Church complex is just the inductive limit of causal cohomology. And if you start at if you erase the first element in the Church, it's just the inductive limit of the subcomplex. You start at K1 in place of K0. Okay, so you get an isomorphism that the sheaf cohomology is the inductive limit of this tensor product of causal complexes, and these are not too big. Okay, and so it shows that this causal complexes that are smaller than the one where you put all the generators of B could be used to determine the cohomology in some bounded region of the R. Okay, and another remark for the computational part is that if you give a V with the dimension equal of the projection equal to di, so this di will be outmost the dimension, then I mean R modulo IV is say V is a variety. This will be finite over the product here. So you can use causal complexes with respect that are shorter. So you can look at that over the ring of this product, which is quite smaller, and this quite if you have something of dimension 1, you just need to work over P1 cross P1 cross P1, and you have a much smaller causal complex than if you live in a higher dimensional space, and this will have to compute the cohomology. Okay. So now let me, well, maybe I'll finish this first part, I mean, by recalling, I mean, quoting some similarities and differences for cohomology between the usual case, or Pn minus 1, and the case where you have products. Okay. So the first thing is that if you look at sheaf cohomology, we have seen that. I mean, for the projective space, you take the one relative to M, and for the other one, we will take the one relative to B, which is just an extension. You take things generated by a thing of, I mean, ideas generated by variables of multiple degree 1, 1, 1. Okay. For the sheaf cohomology of P, I mean, there's quite a difference that we have seen, and it's that I mean sheaf cohomology, except the zeros cohomology. I mean, you have just one for the projective space, which is the graded duo, and which is duo to omega r, so over field. Okay. Anyway, you have a duality with omega r, but in the case of product, you have many homologies, and this will make a real difference. When you want to do some computation, we see that. I mean, you want to understand what happens, okay? In particular, if you want to compute the cohomology from a free resolution, okay, if you have a free resolution of your module, well, it's a quite direct computation in case of projective space. I mean, if you want the cohomology in some degree, you take some graded piece, you could do transpose some matrices and compute cohomology. It's very direct computation. But if you want to do the same of a product, I mean, you have this kind of approach, but it's much more complicated. You do that on this way. I mean, you do that, for instance, P2 product of 2, you do that 3 times, but then you need to put this together with your spectral sequence. It's pretty complicated. This approach do not work that well, I mean, in the case of a product, okay? So it's not that simple. No, we have seen that the Grothendieck formula, I mean, it works in both cases, one with the cohomology with respect to N, the other with cohomology with respect to B. And I will return a bit on that on examples later to complete that. Oops. Okay. It took time to come. Finiteness of dual of cohomology, if you have a field, I mean, this is true of a projective space because, I mean, this local cohomologies are graded duo of some X modules. So you have that the duos are, I mean, if you work over a field, the duos are finitely generated, and this helps a lot to compute them and to understand them. But when you look to the cohomology with respect to B, and we look in this projective case, I mean, the modules are not, even over a field, the modules are not finitely generated, but the duos are not finitely generated either. So, so you don't have this kind of finiteness that you have, and there is no real good repair of that. I mean, well, also if you look at the finite generation of the section ring, and again you assume you have a field, for instance, then if you have a variety and you have no associated points, I mean it's not of dimension 0 and you have no points associated to your scheme. I mean this is finitely generated. Okay. But if you're over a product of projective space, unless you're a product of variety in this product, I mean, it's essentially never finitely generated. So the section ring is not finitely generated as over the polynomial ring. Okay. The vanishing in high degree for coherent sheet, that holds in both cases. I mean, except that, of course, in the product you need all partial degrees to be big enough. The finite generation of graded pieces for coherent sheaves, I mean, that's also true in both cases. But the generic freeness is not true in both cases. So it's true, I think, if you work over, say, a reduced ring and you look at the projective space, then, I mean, the local cohomology, all of it, I mean, you can find an open subspace of A so that it's free over it. This is not true if you're over product of projective space. The cohomology with respect to B will not. It may be that you have no, I mean, open space in A, so that it's free over it. So yeah, there are counterexamples that are not very hard to build. Okay. Now, I mean, the connection between the regularity with respect to B or things that were extended to that. I mean, so you look at the vanishing of cohomology with respect to B, and maybe you put some shift or not. I mean, there are several options, but anyway, they are very close one to another. So this is indeed, I mean, linked to, I mean, the classical case, it's linked, it's defined by the regularity, and it's linked to the linearity of the fact that when you truncate the model in some degrees inside this regularity region, you have a linear resolution. This is one equivalent definition of regularity in the case of projective space of a ring or over a field, okay? In the case of product, that's essentially true also. The relation to Tor module, I mean, it's also essentially true, but in the case of product of projective spaces, you have to look at the Tors with respect to the quotient module, the different set of variables, and not the Tor with respect to all the variables. And so the relation to Betty numbers and to degree of minimal generators, okay, and Tors with respect to, as we have seen, Tor with respect to quotient module M. This is through the connection, but it's the connection with the cohomology with respect to M, which is also multigraded, that is connected to the Betty numbers, okay. So I will maybe finish this first part by mentioning two important tools. I mean, one common important tool that can be used in multi-graded case, and is very important, is shared duality. This holds also, okay. So if you have a one macro scheme or whatever, it should be curved. That's a very important tool that extends perfectly well, okay, to that and work perfectly well. And an additional tool that is sometimes useful is that you can compare the cohomology with respect to two complementary sets. So, for instance, if you have two sets of variables, the cohomology with respect to one and the other could be compared by a spectral sequence that was constructed by Jürgen Herzog and Raimi. Okay, so that's gives also some relation for the cohomology with respect to one set of variables or the others. Okay, so I don't know if there is some question on this first part.
So let's, unless there are any remarks or questions, let's have a 5-minute break then.
Okay. I will come to more, examples and things, to show more on simple, what we could prove or show on simple examples. Essentially to be 4 points, but we'll see. Okay, oops. Let me try to change page. Oops. I have problem to change page now. Okay. So let's look at product of two projective spaces. Okay, and we try. I will partially extend a duality result that one has for complete intersection, and try to explain what happens in this case and what we keep from what happens in the projective space. That's the first thing I will speak about. So this is come from joint work with Navid Nemati first, and it's also, we also worked on that with Laurent Buzet and Gauss-related thing. Okay, so let me first recall what happens in one projective space. Okay, so if you have an ideal defined by R homogeneous elements, okay, and that defines something of codimension R, and let's say we're a field, we work over a field now. Okay, then the causal complex is a graded free resolution of the quotient. Okay, and the shape of the resolution only depends on the degrees of your forms. So for form of the same degree, you have the same resolution all the time. Okay, the Hilbert series is also uniquely determined by the degrees, and you have very simple formula for the Hilbert series. So all of this works perfectly well, and also you have that for any mu. You have just one local cohomology that is not zero, and it's dual, okay, to R mod I with some shift of degree. So if you take the n plus 1, the only cohomology that is not zero, which is n plus 1 minus r of R mod I in degree mu, this will be the dual of R mod I in degree sigma minus mu, where sigma is the sum of degree minus n minus 1 into k. So you have also this nice duality. It tells you that the top cohomology is the dual of this thing here. Okay, one can also say that the top cohomology is just duo of the canonical module, the duo of the canonical module, and this is the canonical module. Okay. Now, in particular, and I will see on examples how this extends. I mean, in particular, I will look at the case of points. And so for points, you have r equal to n, and though you get for any mu, that the Hilbert function of r mod r in degree mu plus the one in degree sigma minus mu, this is the sigma, is always equal to the degree, which is the product of the degrees, d1, dr. So you have this nice formula, I mean, that reflects, of course, the duality behind, okay, that tells you that Hilbert function in degree mu plus the one in degree sigma minus mu is just always equal to the degree, which is the product of the degrees of the forms. So let's look at what we have, I mean, in the case of product of two projective spaces, okay? So now I assume I have an ideal generated by homogeneous elements, so by homogeneous elements, if you want, defining a scheme of codimension R over a field. Okay, but of course now this ideal is never, well, maybe never if M and N are not zero, okay, a complete intersection, okay, ideal. But equivalently, I mean, this causal complex now is not a resolution of our modal, but it's what is called the virtual resolution of our modal IZ. So if I shiftify all that, okay, this gives me a free resolution, okay, of the shiftification. Okay? That's what is now called virtual resolution. Okay, that's always a way to see it. Okay? So all these, if you want, I mean, they share the same virtual resolution, and we want to know what we get from that. Okay, so in restricted degrees, okay, well, you have a spectral now always. I mean, you have this cohomology with respect to B, and you have a spectral sequence like this. Okay, because the thing is that we assume this is a resolution outside V of B, so it will tell us that for positive Qs, I mean the homology of the double complex that gives that is just the cohomology of R mod I. So we have an instrument to control the cohomology with respect to B of R mod I through the causal complex taken on the cohomology of the ring. So that's what we explore it. Okay, this exists also one projective space. Here it's a little bit more complicated. In a usual case, this thing, if you replace B by M, it just gives the usual thing. It proves that it's a regular sequence and it gives everything. Okay, there is no problem there. Okay, but here it will help us to understand what happens. Okay, so this will provide a duality as in the case of a projective space, but only in restricted degrees. And we'll see what this, okay? And for that, I will concentrate, I mean, to the case R equal M plus N to describe completely what happened and show some examples, okay? But in some degree, I mean, we have a general result, but that's not a problem, okay? So assume I have a set of points. And so what will be this restriction on degrees? So it will come from the support of the causal of the cohomology in the causal complex. Okay, so I will call gamma I, and we'll see on the example just after, the support of these two local cohomologies of some causal homologies. Okay, so one can, I mean, let me just show what it is, what it looks like. So we have this thing. Okay, just recall what is there. And I will take an example. So we take we look in P2 cross P2, so M equal N equal 2, and we take, so it's of dimension 4, and we take 4 forms of by degree 2, 2. So this sigma will be 4 times 2, 2, 2, 2 added 4 times, minus 3, 3. That will be the same, the invariant, okay? Sum of the degrees minus, I mean, what is called the, plus the A invariant of the thing, the shift that corresponds to passing from the ring to its canonical mode. Okay, so this will be 5, 5. And so that's the picture. So this support of causal mode in that case looks like this. So you have, I mean, I pictured the 3 region, gamma I. I pictured gamma -1, gamma 0, and gamma 1 because these will be the one that will be useful to us. Okay. So this gives 3 regions, okay, of this type, where you start from a point and then So you see very well on the picture what these look like. And you have this degree sigma, and okay, which is here 5, 5. Okay, and so now we have a theorem about that. So assume that we are in our situation, and for simplicity, I took, in the case of points, and I take everybody of the same degree, dE, okay? Then you set sigma equal to that, okay? And then the theorem says the following. First, if you're not in the region gamma 1, so there are 3 regions, I will show after I pack the picture. Then the ideal is saturated. So the ideal is equal to its saturation. So the defining ideal of the points is equal to the ideal itself, okay? And so in particular, the Hilbert function of the scheme is, I mean, of formula Z is equal to the one of formula. We are interested in understanding the Hilbert function of the set of points in this, okay? The second thing is that if mu is not in gamma 0, then we have this thing like before. We have this kind of duality, okay? That the Hilbert function of Z plus the Hilbert function of sigma in degree mu plus the Hilbert function of Z in degree sigma minus mu will always be equal to the degree. And in this case, the degree is the binomial coefficient m plus n times dm times den. I mean, that's a general computation, and that you can compute always the degree in this case, and it will be the, in fact, it will be the sum of the product of the di and the ej's if we have different degrees, but here all are the same, so we have a very simple formula. The third thing is that now if you're in gamma 0, but you're not in gamma 1 nor in gamma minus 1, then you also have a kind of duality. I mean, so you don't really have your formula, but you have that the sum is equal to this, and you have a correcting term, but the correcting term only depends on this mu, and we'll see a little bit about the dependence of that. So let me show on the picture before what this says. So you have this, okay? So this says that if you are outside the green region, so if you're not in the green region, then your ideal is saturated, okay? So if you're, and you see the green region means that the region where not saturated, 1 degree is big, the other is small, one way or another, okay? With some, of course, precise control on that. It means here that if you have something in the saturation, for instance, the degree in X, because here we have symmetric degrees, the degree in X should be at least 6, but the degree in Y at most 3, or the opposite, okay? You have nobody that is not in one of these 2 green things, okay? The second thing is that outside the blue region, okay, you have this symmetry, that the Hilbert function in degree mu is plus the Hilbert function in degree sigma minus mu is equal to the degree. And in fact, one can write this in terms also of a duality, a more precise thing, I mean, about the quotient there and the other place where you have one map and the joule. Okay, so it could be written in more. Okay, and the third thing is that if you look in the rectangle, okay, where you, or here it's a square that you make from 0, where the corners are 0 and sigma, okay, the Hilbert function only depends on EE, okay, so because, I mean, your ideal is saturated, and we have this formula that gives the Hilbert function. So you see you have the square here, and we see that just an example of size 5, okay, where the Hilbert function have this kind of this duality or semi-duality property, and then everything, and the function is always the same, okay, so like in the case of a projective space, always the same function and the duality, and you have the green parts which are more far away, where these do depend, in fact, on the set of points you have, and will reflect some geometry. I will explain that just now. Okay. So let me give some tables, okay, so you can see what it looks when you want to compute some examples, okay. So these are 2 examples of these things by 4 form of by degree 2, 2. And I show on this what are these regions. So you have the square. So the square, you see it, on this, I mean, it's the square, the 6 by 6 square. I mean, the corners are 1 and 95. And when you sum of a diagonal, I mean, you have this 95 plus 1, 93 plus 3, 90 plus 6, or in the middle, I don't know. I mean, so you have a center of symmetry, okay? And you have that the sum, I mean, is always equal to 96, okay? And now you also have, I mean, this blue part of the square, where you have, for instance, the first, it's the same first and second, 45, 63, 15, and 21, okay? And then you have values of epsilon that tells you that there is a difference between the dimension, okay? And these values are 1, 3, 3, 9. And you can remark, and this is I didn't put in the term, but this 1, 3, 3, 9 is just a block at the origin also. Okay, so you can express everything in this block in a simple way. What are all these numbers? So what is the dimension of the quotient? And this dimension of quotient, you have some duality, and this dimension of quotient do not depend on the forms. But if you go out of that, okay, first, I mean, by the term before, you see that everything that is in green, okay, has to be 96. I mean, so the Hilbert function has to have reached its value because you have a duality if you're not in blue, and this is due to something, okay, I mean, dual in the sense that this plus what is at the opposite compared to sigma should be equal to 96. And when you do the symmetry part with center sigma, you find 0 because you're not in the positive quadrant. So all what is green should be in 96. So this gives a strong result about the regularity of this function. I mean, so everything that is not in the square, and so all the 96 that you see in green and above or on the right are always there, okay? And now what varies is just what you have in blue, okay? And this depends on the form that you have, okay? And we see what is the information that one get from that, okay? So we have two different ones. I mean, things are more visible if we replace the Hilbert function by its complement. So by the dimension of H1b, we have that the Hilbert function is equal to the degree, okay, minus the dimension of H1b. So if you prefer, the dimension of H1b plus the Hilbert function is equal to 96. So taking out 96, taking 96 minus the function gives you a better picture where you, by what you have seen, you have just things in blue and in black. The black thing has this duality, and the blue thing depend on the different set of points. Okay, so these written this way, these are my two sets of points and their Hilbert function. Okay, it continues. Okay, so now on this, I mean, I will give okay. Yeah. Okay. Now I will explain a little bit the information that one can extract to that by some terms. Okay. So first, okay. Sorry. Before that, I return to what I explained before. I mean, the connection between cohomology and Betti numbers or resolution. Okay. So for that, I have taken I think it's I don't know if it's not one of the two examples. It's another example of a complete intersection. Okay, and on the left you have the cohomology table. So this gives you the numbers that you see are just the dimension of the first local cohomology with respect to m. Okay, I shift the degree by 1, 1 to show that when you shift by 1, 1, you have the same picture. And on the right, you have the resolution, but this is a finite set of points, so you can take the resolution over P0 cross P0 over just the point, because it's a finite point. So I prefer to do that. I resolve over the polynomial ring in two variables that are of degree 1, 0, 0, 1. Okay, to have a simpler table. Okay. And so you see that you have a connection between the torus on the right and the cohomology on the left. I didn't put the numbers for the dimension of C1b, C1b1, C1b2, but the shape is the same. You see that the also that the cohomology with respect to M correspond to the torus with respect to M, okay, 1 to 1. And the corner numbers that I have underlined, this 3, 3, 1, 3, 3, they are the same also. They have to be the same. Okay, so you have that the extremal cohomologies with 3, 3, 1, 3, 3 is the same as the extremal Betti numbers. Okay, and over P0 cross P0 also you see this duality, takes a slightly different form. Okay. Okay, now let me show in this case the resolution, as you see, it's a little bit bigger over P2 cross P2. So if you resolve the same example of P2 cross P2, so you have a longer resolution, okay, with 6 terms from F0 to F5. And what is displayed in this box in each by degree is the number of summers that you have for F1, F2, F3, F4. It happens that in this case, there is just one by degree where you have some summons of F1 and F2, else it's disjoint. So it's easy to show with different colors that you have in different places in the resolution, okay? So one sees that, of course, this is more complicated, but one sees again that you have, I mean, that first one sees that you have, inside this resolution, you find again a causal complex, which is this diagonal 1, 4, 6, 4, 1, okay, but it's split into two because the first three guys appear in F0, F1, F2, F0, F1, F2, and the other one appears in F4, F5. Okay, so there is a splitting there, and so there is two parts of causal. Okay, and the rest you see this thing that the first generators and CGG, there no doubt, appear in degree at least 6 in X. Okay, and at most 2 in Y. And of course, when you pass to CGs, you increase by 1. But you see that this red thing, 1, 15, 9, and the 3, they have to appear in degree at least 6 and a degree at most 3. Okay. One also sees, and that's a general phenomenon, that the last degree where things happen in one direction is obtained at here the second step. So it's the F2 bounds the regularity in, say, the X one set of variables that way. Okay, so the if you want the extremal, the last place where you have some the last shift in one direction or the other can be seen from the first 3 steps in the resolution, F0, F1, F2, and that's general for that. Okay, so one sees, I mean, constraint on that, and you also remark that the extremal Betti numbers does not depend. I mean, they are still there with 3, 3, 1, 3, 3. Okay, they are extremal, and these appear in wherever you resolve. Okay, so these are general facts. I mean, that are not hard to show. Okay. So let me now give 2 formulas that to create Hilbert function and cohomology, which are, we have seen one, okay? So let me recall this one. So in this case, I took the simplest case. So these are points. So the Hilbert polynomial is just a degree, just a fixed number. Okay, and I will, for simplicity, I will set small HIA of mu nu for the dimension of the ith cohomology in A of the quotient of R mod Z in degree mu nu, because I have to use these for several cohomologies. So the theorem is like this. I mean, the first thing is that we have seen is that if you have Z of dimension 0 and any mu and nu, the Hilbert function in degree mu nu is equal to the degree of Z, the dimensional value, minus the dimension of H1b in this degree. Okay, this was the formula. Okay, so it's the correcting term. Okay. The other formula expresses the Hilbert function in terms of the defect of the Hilbert function in terms of H1 in M and H2 in M, which is more interesting, in fact, in practice. Okay, so it says that if you want to know the Hilbert function in degree mu nu plus the degree of Z is the Hilbert function in degree mu and anything sufficiently big in u plus the Hilbert function in degree sufficiently big in mu and nu minus h1m plus h2m. Okay, we have seen in these pictures, maybe I can show the picture, I mean, whoops, where is it? Here, that the Hilbert function, I mean, stabilizes. I mean, for instance, the first example you see above goes to 72 and 24. Okay, so this stabilizes. Okay. Okay, let me return. Okay, so these are these eventual values. Okay, I will express, and now these eventual values. So if z is reduced, as you have to modify a little bit the statement, so I prefer to show the reduced case. If z is reduced, the value at infinity, when nu is big enough, is just the sum of the Hilbert functions of the fibers on the projection. So you project one direction, okay, you look at the fibers, you have Hilbert function for the fibers. Of course, if you have just one point, it's just the, I mean, 0 and 1, but you have, and so if you sum this Hilbert function for all the fibers, this gives you a function, okay? And that's the value at infinity of your, so that's the eventual value of your function, okay? When you get one sufficiently big and you look in terms of the other, okay? Of course, it's true also the other way around, okay? If it's not reduced, you have to modify a little bit. You have not to work over the fiber, not over the point downstairs, but over the local ring downstairs. So it's a little bit different. But if it's reduced, it's just this, okay? Okay, so PIs are the projection of the P1 and P2 on the different factors, okay? So it's, okay, and of course you look at the fiber as an element of PM cross Y, so as an element of PM, okay? And as a corollary of that, okay, you have that if for instance, the second projection is 1-to-1, okay, the second projection is 1-to-1 if and only if the Hilbert function, when you're far enough, okay, is equal to 0 in negative degrees and degree of z in non-negative degrees. So it jumps from one to another, because to say that the projection is 1-to-1 says that the fibers are just one point. Okay, so the sum of the thing would be just that, and you have this equivalence. Okay, so that essentially follows from the theorem above. Okay, so I reproduce this formula, and now you have these things. Okay, and we have the following. So due to this formula, it's interesting to understand where H1m and H2m are supported. And it turns out that, I mean, under a weak hypothesis, one can say things about that. So if you have a z of dimension 0, the first thing is that the support of H1m is always in n squared. So it's always in the non-negative part, okay? We have seen that above in the examples. I mean, but this is, okay, this, maybe I could return to this. Okay, we've seen that. I mean, the local cohomology here, you see, I mean, this is in the non-negative part you see on the left. Okay, so that's a general thing. I mean, it could be reduced or not reduced, whatever. I mean, I return to my thing. Okay, the support of H1m is always in n squared. Okay, the second thing is that the support of H2m is stable under the elimination of minus the subtraction of any number, so it's stable, but on the other side, okay? And the important, I mean, and in many cases, the support of H2m do not intersect the support of H1m. So it does not intersect n squared. So this is the case, for example, if you have a reduced scheme and you have no point x that has the same projection on the first factor as another point, and the same projection on the second factor as another point. So if you have no triplet of points, so that one project the same way as the same projection as the second on the second projection, and same projection as first one on the first. So if you don't have a triplet like this, okay, then you know that H2M of R minus Z do not insert. So they are distinct, okay, in this case, okay. And you have other condition that give that. I try to give a pretty simple one. So with some genericity on the point, but not too much, okay, you have that H2M and H1M do not have one, they are never non-zero together, okay? Okay, so well, if further, that's so Mark, if further both projections are one-to-one, then the cohomology with respect to M and B in non-negative things are the same, and the H2M is just the following thing. I mean, the dimension of H2M is just the degree if you're below -1, and it's 0 else. Okay, so you have a very simple H2M in that case if you have different projection. So the thing to analyze in that case is just H1M, which is harder to understand. Okay. So to conclude, I would say this says that the Hilbert function of R mod Z determine this difference. Okay. Under my assumption, you know that this support as distinct. So from the Hilbert function of R mod Z, you can compute H1M and H2M, and that's quite useful in practice. Okay, because you have simple access to the Hilbert function. Okay. And in general, I mean, if it's not as good as I explained, I mean, if points are not in sufficiently general position, one can try to get information from the H2M of R mod Z, and that's what we do in the other case by knowing that it's the KU of the omega of R mod Z. Okay? And finally, I mean, so we know we have an equality. I mean that the support of H1M union the support of H2M, if you subtract n squared to that, I mean, it's the union of support, and you have the same external elements, okay? So this is this Hilbert function, I mean, under my summer, I mean, you are in slightly general position, and from the Hilbert function, essentially you can deduce in most cases what are H1M and H2M, and from that, you know where are the tors and all that. So the Hilbert function reflects all that, okay? And last remark is that, I mean, for points, you have the inclusion, I mean, you always have the inclusion that the support of the cohomology with respect to M is in the intersection of the cohomology with respect to B1 and the one in respect to B2. And in the case of points, we can prove out of what we know that this is always an equality, but we don't know in general if this is always an equality, I mean, for arbitrary dimension in product of two projective spaces. So that's one of, for instance, one of the open questions we have. Okay, I think I'll stop here. I think, yeah.
Okay, thank you very much, Marc. Thank you very much for the nice talk. Are there any questions?
Yes, no? Welcome.
No questions?
No questions?
No questions? Have you looked at more than products of two spaces?
For some things, yes. I mean, for instance, for this last formula, thing like that. I mean, first, I mean, results about, support of tors and support of cohomology, all that work in any product, okay?
Right.
But also this, oops, I don't know, it refuses to change sign, okay. For instance, this formula that you have on top, where the Hilbert function, where the degree is the, you can express from the Hilbert function these things, okay? This extend to more, okay? Okay, but I mean, the formula is not, I mean, it's a bit, I mean, you have to sum you have to do a recursion on things, so it's not as nice, but I mean, you can, at least for 3, it's manageable to do. The problem is that when you have many, I mean, you may have formulas, I mean, but you have multiple sum or recursion and thing, and it becomes a bit tricky to handle really the thing, even to represent I mean, things, I mean, a three-dimensional more or less you can represent, but then, I mean, you have, I mean, it becomes hard for you to imagine what's going on. I mean, it's
Yeah.
more, but I mean, the formalism works pretty well. So,
Mhm. Also, the formula in terms of fibers, the second line of that slide, that works also.
yeah, this works also. Yeah, you will have to look at the different fibers and things. Yeah, to the different projection. If you don't have points, for instance, if you want to do that for curves, you will have a bit of a writing like the first line that we see.
Mhm.
But the thing is that first you have a Poincare characteristic with more guys, and H1, H2, H3 of them. And the other thing is that you have contribution, but you do, I mean, that are, I mean, not so simple. You cannot, for instance, the second line I cannot do. I mean, you have things that are, I mean, in that case, you have things that are polynomial with coefficient that are not polynomial and things like that. So then you have to express these. I mean, and I don't know how, I mean, there is a same formalism, but I don't know how to express this. Here you have a nice formula that says it's the sum of things of all the fibers. But when you have a curve, you don't have this. I mean, so you have to do something along the curve and the fiber above the curve. And I don't have such a formula for that. You have a same kind of writing that it could be written in a unique way in some way, but the things in the expression, I don't know all what they are. And if you have many things and higher dimension, I don't know really how one should write it. I mean, so, but if you move a little bit, you have some formulas, but what is the expression, what it means, it's not as clear. So in that case, I mean, or in case of points, I know what it means, but in simple terms.
Thanks, Mark. There is another question. The question is there anything of the case of complete intersections that holds for more general toric varieties? Even the simplest non-standard C2 graded case you can think of.
I don't know. I mean, I really, for these things, I mean, this understanding of complete intersection, what it means, I mean, I just look at the case of products. I mean, even products of two. I mean, of course, formalism work the same for products of more. With Navid and Laurent, we looked at product of more and did some duality and things like that. It was not this case. It was not points. It was for the empty sets. We looked at it was for doing elimination theory. So we looked at when you put as many forms as the. So I mean, it's a bit different, but the formalism is the same. And no, for toric, I mean, for toric, I would try to do the same thing. I mean, you have the same kind of formalism thing. I mean, but I don't know. I don't know. I never worked with that. I mean, even with, I mean, even with three projective spaces or things like that, it's not so nice. I mean, to understand exactly what happens. I mean, so it's the problem. It become a bit tricky to have a picture of exactly what. I mean, there are some, I mean, some pieces where you can say on between these two small blocks I have dualities, but to know exactly how far you can go, I mean, and exactly what you have, it becomes a bit tricky because also when you have different multi-degrees, I mean, things mix up more. I mean, the pictures don't look so nice. I mean, of course you have statements, but things are not always very nice looking. So that's why also I'm restricting this to some simple degrees where things are looks pretty.
Hey, thank you. Are there any other questions? Then let's thank Mark again. It was a nice talk.
Thank you for the invitation.
Fun.
Thank you for the invitation.
You're welcome. And we will have a break over the semester, over the summer, and the seminar will resume in the fall, probably beginning of the fall, hopefully. So you should all have a good summer till then. Thank you.
Thank you.
And Mark, I'll see you in India very soon.
Yes, soon,
Yes,
soon,
right,
2 weeks from now. Good. Thank you.
Thank you. Thanks.
Thank you.
Bye, Bernd.
Oh, bye, Javid. Yeah.
I was waiting for you to stop the recording, but it keeps going.
Oh, it keeps going. I see. Okay. Oh, you know, I don't even know because Carl is in charge of the recording, so I don't know
Okay.
how to stop that. How to stop that?
I catch up with you later then.
We catch up, Javid. Yes, great, great. Good to see you. We'll be in touch.
Good to see
Okay.
you too. Bye.
Take care. Take care.